Hi everyone, today we're talking about exponential and logarithmic equations in section 3.4. Alright, well, what is an exponential equation? An exponential equation is an equation that contains a variable in the exponent. So examples, take a look at this one. 3 to the power of 2x plus 3 equals 7. Or we have ones where we have exponents in the variable exponents on both sides. Well, what's one way to solve this? One way is what we call the one-to-one property. One-to-one property basically means if you can get your equation to reduce to a form such that the bases on either side of the equation are identical, then you can simply set the exponents equal to each other. Or if the logarithms are equal to each other, then you can set their arguments equal to each other. So let's solve some exponential equations using this one-to-one property. So what I want to do is I want to make the bases on either side of the equation equal to one another. It's not necessary that the base is the most simplest form possible. They just have to be equal. So here on the one side I have a base 4, on the other side I have a base of 16. Well, it turns out that 16 is actually a power of 4, right? 16 is actually 4 to the power of 2. So I rewrite my 16 as 4 to the power of 2 times x minus 3. Now that my two bases are the same, all I have to do is simply set my exponents equal to each other. And look at that, it turns into a simple algebraic equation where x plus 2 is equal to 2x minus 6, 8 is equal to x, and that's your answer. Now, we learned in the previous lessons in this chapter that exponential functions have a domain of all reals. That means any number is going to work for exponential functions, so there's no need to check. It's not going to be that way for the logarithmic equations though. All right, let's do another one. Here I have 2 over 3 to the power of x minus 5, 9 over 4 to the power of 3x minus 4. Well, how do I make these two bases equal to each other? Well, if we look more closely at the 9 over 4, right, how do we get 9 over 4? Can we relate that to 2 over 3? Well, let's see. In order to get 2 over 3 to equal a 9 and a 4, well, first, right, it looks like this needs to be flipped over. I need to get the reciprocal. So that is a negative exponent. And now, if I have a negative exponent, the 3 will become the numerator, so I can match it with the 9. And what do I do to the 3 in order to make it a 9? Well, how about I square it, right? So let's think about that. Is 2 over 3 to the power of negative 2 9 over 4? It sure is. So let's rewrite this. This one remains unchanged. But this one, I have 2 over 3 to the power of negative 2 times 3x over 4. Well, now I set my exponents equal to each other. What do I have here? Negative 2, and here we have a 4, so that'll be a 2 here. So this is negative 3x over 2. Simplifying further, 2x minus 10 is equal to negative 3x. 5x is equal to 10. And x is equal to 2. All right, let's do another one. Now, here I have 4 to the power of x equals 13. This one is a little bit different. Why? Whereas before in a and b, I had exponents which contain variables on both sides of the equation. Now, I only have such an exponent on one side. So what am I going to do to get rid of this? Well, what's the inverse of an exponential function? a logarithm, of course. So how do you get rid of this one with a logarithm? Well, you take the logarithm of both sides, but you have to be careful that you make the base of the logarithm the same as this base. So now it's log base 4 of 4, which goes away, and I have x is equal to log base 4 of 13. Okay, you are more than welcome to leave it this way. If the instructions call for a decimal answer, then you can plug it into your calculator. Okay, here I have e. Well, what gets rid of e? Log base e, which is also called ln. So I take the ln of both sides, which means 2x plus 1 is equal to ln of 8. Now, solving for x, subtract a 1. 2x is equal to ln of 8 minus 1. Divide everything by 2. X equals ln of 8 minus 1 all over 2. All right, so those were exponential equations. What if we're dealing with logarithmic equations? Well, these have a one-to-one property of their own. And this says that if the logarithm has the identical base on both sides of the equation, so log base 2, then you can simply set their arguments equal to each other. Okay? So let's take a look at this one. Here I have 2 ln of x is equal to 18. All right, before I even do anything, I need to isolate that ln. So I divide by 2. ln of x is equal to 9. Now, what gets rid of ln's? Exponentials. What I'm going to do now is I'm going to make this an exponent of an exponential. So e to the power of ln of x, I raise it as an exponent of e, and it becomes e to the power of 9. These go away. X is equal to e to the 9. And that is way too big a number to expand. So e to the 9 is just fine. Okay, what about here? We're going to isolate the logarithm. So I'm going to subtract 7, making this negative 3 log 10x equal to 6. I'm going to divide by negative 3. So log 10x is equal to negative 2. Now, how do you get rid of this one? What's going on here? What is the base of this log? Well, if there is nothing written, it's a base of 10. Log base 10 of 10 will give you x equal to negative 2. Okay, let's do another one. All right, here I have a log base 5 of x to the 4. So what I need to do first is I need to take this and I need to get rid of the log. To do that, I have to make it a power of the base 5. So the entire thing here will become an exponent of base 5. So this is 5 to the power of log base 5 x to the 4 equal to 5 to the power of 20. So if you see in the purple, log base 5 x to the 4 equals 20, that's the main equation that we started with. The entire equation has now been elevated to an exponent of base 5. When we do that, we can get rid of this, and x to the 4 is equal to 5 to the power of 20. Okay? Well, now, how do I get rid of an exponent of 4? Well, I take the whole thing, raise it to the power of 1 over 4. So I have x is equal to 5 to the power of 5. And again, this is good enough to leave like this. All right. What about here? If you look at this, you have log base 5 and log base 5. They're identical to each other. So what I'm going to do is I'm going to set the arguments equal to each other. So I have x squared plus x is equal to 20. Now this looks like a quadratic equation. Well, it is. I bring everything to the same side, set it equal to 0, and I have factoring it, x plus 5, x minus 4 equal to 0. So x equals negative 5 and x equals positive 4. Now, in a case like this, remember that the domain of logarithms is not all reals, right? In fact, logarithms only exist after the asymptote. So especially when you get two solutions, you have to plug it in and check. So let's check these. X equals negative 5. Does that make sense? All right, so here, we're going to plug it into the main equation. So log of x squared, 25, plus x minus 5. Is this equal to log base 5 of 20? Well, it looks like it would be. And now let's check x equals 4. Is log base 5, 16 plus 4, equal to log base 5 of 20? Well, looks like that one is too, so both of these are the answer. All right, let's do one more. Okay, here I have a logarithm here and two separate logarithms on this side. Well, I can't have that. In order to use the one-to-one property, I need to have one logarithm here and one here. So what I have to do is I have to condense this one. So now I have log base 2 of 5 equal to log base 2 of 10, and since I have a minus sign here, this x minus 4 will become a denominator. So now I can set the arguments equal to each other, and I say 5 is equal to 10 over x minus 4, cross multiplying, 5x minus 20 is equal to 10, 5x is equal to 30, and x is equal to 6. And if you quickly put this back into your equation and check, you will see that it does check out. Okay, moving on, taking things up a notch. All right, here we go. Now I have two different bases, and I have no way of making one into the other. So I need to get rid of both of them. The way I do that is I want to take the ln of both sides. What I have here is ln of 3 to the power of 6x minus 3 equal to ln of 2, 4 minus 4x. Okay, now remember these are exponents. They're going to come down. So we're going to have 6x minus 3 times ln of 3 equals 4 minus 4x times ln of 2. I distribute the ln into the parentheses. So I get 6x ln of 3 minus 3 ln of 3 is 4 ln of 2 minus 4x ln of 2. Now, I need to collect all the terms that have an x onto the left side, and everything that does not have an x onto the right side. So this will move over, and I will get 6x ln of 3 plus 4x ln of 2. This term will move over here, so I will get that equals to 4 ln of 2 plus 3 ln of 3. Now, can I factor out an x? Sure I can. I can factor out an x, and I get 6, let me write it off to the side here. Six ln of 3 plus 4 ln of 2 equals to 4 ln of 2 plus 3 ln of 3. All right, what do I do now? I divide by 6 ln of 3 plus 4 ln of 2. So this goes away, and I have x equal to. Now, let's do some condensing here. This will become an exponent, so it's ln of 2 to the 4 plus ln of 3 to the 3 over ln of 3 to the 6 plus ln of 2 to the 4. Can I condense further? Sure I can. This is ln of 2 to the 4, 16, times 3 to the 3, 27, over ln of 3 to the 6, times 2 to the 4, 16. Will those go away? Sure they will. Well, what do I have left? I have ln of 27 over ln of 3 to the 6. So let's just work over here. Ln of, I'll write it here. And there's my answer. All right? Okay, let's do this next one. Same situation. I'm going to take the ln of both sides, and if you don't mind, I'm just going to start from here. Ln of 6 2x plus 4 is equal to ln of 5 negative x plus 1. So 2x plus 4 ln of 6 is equal to negative x plus 1 ln of 5. 2x ln of 6 plus 4 ln of 6 equals negative x ln of 5 plus ln of 5. Now, I'm going to take everything that has an x to the left side. So that's 2x ln of 6 plus x ln of 5 equal to ln of 5 minus 4 ln of 6. Factor out an x. That gives me 2 ln of 6 plus ln of 5 equals ln of 5 minus 4 ln of 6. So x equals ln of 5 minus, let's condense, ln of 6 to the 4 over, this is going to go up there, ln of 6 squared plus ln of 5. Condensing even more, x equals ln of 5 over 6 to the 4 over ln of 6 squared is 36 times 5. Okay, that's my answer right there. All right, I know it's a little bit lengthy, but if you keep at it, I think you'll see the utter joy in it. Okay? All right, let's take a look at this one. Now, this one is called quadratic form. So do you remember when we had equations like this? X to the 4 minus x squared minus 2. We can factor them in quadratic form. So it would be, instead of x and x, it would be x squared and x squared, right? And then we would have to find two numbers that multiplied to -2 but added to +1 like this. Well, what do I have here? I have e to the x and e to the 2x. Is that anywhere close to what I have in my quadratic form with the algebraic equation? Well, let's see. If here I have x squared, here I have the square of x squared. So this is really x squared squared, right? Well, let's see if I have the same thing there. If I have e to the x, and if I were to square it, what would that be? Oh my goodness, it would be e to the 2x. So here I have the square of e to the x. In other words, I can write this as e to the x squared minus e to the x minus 2 equal to 0. Now, just like I did here, when this was x to the 4 minus x squared, when I factor, I take the square root, x squared, and x squared. So let's factor that. Everything can reduce to quadratic form, right? All right, if I have e to the x squared, what's the square root of e to the x squared? Well, it's just e to the x, e to the x. Because look, now when you multiply e to the x times e to the x, you get e to the 2x. Now, I need two numbers that multiply to -2 and add to -1. Just like that. Hey, look, it's the same. Now, I need to solve these two mini little equations. So let's go ahead and do that. Here, I'm going to have e to the x minus 2 equals 0. E to the x equal to 2. How do you solve this? You take the ln of both sides. So I have x equals ln of 2. Well, what about this one? E to the x equals -1. Well, if you take the ln of both sides here, you end with x equals ln of -1. And what is ln of -1? No solution. So the only answer is ln of 2. All right, let's take a look at this one. 40e to this crazy number 0.6x minus 3 is equal to that. Well, what am I going to do here? You know what? First, let's isolate that term with the x. So 40 e to the 0.6x equals 240. Okay, now what? Can I divide by 40? Sure I can. When I do that, e to the 0.6x will become 6. And now, how do I get rid of an exponential? With an ln. So 0.6x is equal to ln of 6. X equals ln of 6 over 0.6. And if you were to use your calculator, this would equal to 2.99. Alrighty. Now, there's just no end to the fun here. One more. I have ln of something minus ln of something else. So what I need to do is I need to condense this first. Okay, let's do that. There is a minus in the middle, so it'll be ln of a fraction, 7x plus 3 over x plus 1 equal ln of 2x. Okay, now I can use the one-to-one property and set the arguments equal to each other. So 7x plus 3 over x plus 1 is equal to 2x. Let's cross multiply. 2x times x plus 1 is 2x squared plus 2x. So 2x squared minus 5x minus 3 is equal to 0. Let's factor this. 2x and x plus 1 minus 3. And here I get that x equals negative 1/2 and x equals 3. All right, well, let's check. When you check, negative 1/2 will not work because here you get ln of a negative number. So the only solution is x equals 3. And one more. We're going to condense this one as well. So it'll be log base 12, 12x times x minus 1 is equal to 12. Now, how do you get rid of a 12? How do you get rid of a log base 12? Well, we make it a power of 12. Okay, now these will go away. So I have 12x squared minus 12x is equal to 12 to the power of 12. And this is one where, again, you would have to factor in quadratic form and find the answer. And I will leave it at this. Most of the problems you will have are more manageable than this number here. Let's go on to this next one. Well, it says to use a graphing calculator to solve this one. So what I'm going to do is I'm going to plug this into the calculator. Now, there are several ways you can do this, okay? One way is to plug this entire thing into y1, but to plug it into y1, what you would have to do is you would have to bring this over to the other side. So it will be log of x minus 15 plus log of x squared minus the square root of 2. And I'm going to do zoom 6 because I don't know where my windows were before. Okay. Let's see. See anything here, right? Okay, so what's going on here? One thing that could give you a clue is that here we have log of x minus 15, right? That means there is a shift 15 units over. Well, why don't I take my window over there then? So why don't we go x min from 0 to, oh, I don't know, let's make it 20. Graph. There you go. You see a little bit of something there, right? Okay, so does it cross the x-axis though? What's happening there? Let's see. Let's trace. Okay, so at x equals 10, yeah, there is not going to be anything because this doesn't start until all the way here. So let's just keep moving, keep moving, keep moving, keep moving. Okay, so here's the trick. You see how at y equals 15.5, it's a positive value for y? Go to the left, and there is nothing there. So now I want, ooh, look at that. There is a negative value there. That means there must be a 0, right? Because it switches from negative to positive. Okay, this is a horrible window because I can't see anything, right? Everything up here and everything down here is just being wasted. So why don't I go back to my window and let me modify them a little bit more. Let's go from negative 1 to 1. Really, all I care about is, you know, that little strip where y equals 0. So this should be good enough. Can you see how it dips down below a little bit? That's good enough for me. Second calc, 0. Now it says, where is your left bound? Well, I'll take you to my left bound. Let's see. Going there, past it. There we go. That's my left bound. Right bound, good enough. You want me to guess? Sure. There it is. That's my 0 at x equals 15.11. And the way I'd like you to write it is 15.11, comma 0. Now, that was one way that we could have solved this, okay? Another way is you could not move this root 2 over, and you could plug the left side of the equation into y1 here, just like we did in the 2 sections ago, actually. So I'm going to delete this. Okay, enter, and just type in root 2 in y2. Now I'm gonna check where these two graphs intersect, right? So we either move this over, graph it, and see where the x-intercepts are, where it crosses 0, or I graph them separately and see where the two of them intersect. So let's see. If I do zoom 6, all right, that's not going to give me anything because I already know that it's at 15. So let's go here, window. And again, why don't we go from 10 to 20 this time. And here, since we want it to cross y equals root 2, right? I don't need this negative 10 to 10. All I could do is, let's say, negative 1 to 3. Graph. Okay, there's the first graph, and there's the second graph, and they barely cross over there. All right, so let's see where they do cross. Second calc. Now I want the intersect feature. So number 5. Is this the first curve? Yes. Is this the second? Well, let's see where the first curve is. There. Yes. Is this the second curve? Yes. Guess. Sure. And there you have it at 15.11, right? And again, you want the x value from there. X equals 15.11. All right, everybody. Again, the highlighted ones can be numbers where you can start off. And I will see you in class.